This is a continuation lecture of Chapter 9. In Chapter 9, we originally set out to lay out the similarities between linear and rotational motion, which is contained in the summary from the first lecture of Chapter 9. But today, we want to see if we can unlock another relationship which is not necessarily present on the surface. However, it is one that we might all be familiar with in our everyday language. So, let's take a look at this circle that we have drawn here. And if we have 2 points labeled as number 1 and number 2. And since we're talking about circular motion, if we're going to travel from point 1 to point 2, well, in some ways, we're going to draw out a triangle which looks like this. Now, in reality, we know that this triangle is really going to be a little piece of arc length along the circle. But we're going to do a limiting process at the very end, which we can say that if we let the distance between R1 and R2, namely delta S, become very small, then this would really be a really tiny triangle. Now, that is one triangle that we can draw, but there's actually another triangle that we can draw by our knowledge of vectors and moving them around from tail to tip. This will be a little bit difficult to draw, so I apologize in advance. But if instead we say that, well, at each one of these points, namely R1 and R2, at their respective S1 and S2, each one of these is going to have its own velocity vector along the circle, which the velocity will always be tangential to the circle, which means that at the point 1 in green, this will draw out a velocity vector, which looks something like this. At the point R2, the velocity vector will be something like this, namely always tangential to the circle. So, if I take these vectors and I draw them from tail to tip, then what we can see is we can make a new triangle which looks something like this, where we have our V1 and our V2 and our delta V vectors drawn respectively. Now, this is very interesting because since these are generated from the same motion, namely from moving from point 1 to point 2 along R1 and R2, with velocity V1 and V2 yields a delta V or a delta S. These are two triangles that are generated from the same system, so we say that they are similar triangles. So much like how we use this piece of knowledge, namely that S was equal to theta R, from our knowledge of high school trigonometry, we can now use something else from our high school trigonometry, namely the knowledge of similar triangles. So, if we use that knowledge of similar triangles, we know that in two similar triangles, we can draw conclusions about places in the triangle that are proportional to one another. So we can make a couple of relationships, but let's just go for the obvious one. The dashed lines, and let's say the line on the right, on each of the green and red triangles respectively, we can make the conclusion that delta V is to V1 as delta S is to R1. And this, although it seems like a harmless relation, is going to be actually very important, and let's see why. So if we come over here and we give ourselves some more room, let us remind ourselves of the relationship that we have just built, namely that delta V over V1 is to delta S over R1. But we said that we're going in circular motion, so R1 is really the same as R2, which we could just call R, since we know that in circular motion, we're always on the circle, and the radius has to be constant. Well, if that's the case, then instead of just having the R1 there, we can replace it by just an R. Now, this is actually very powerful because we can have a little bit of fun with algebra. Since the deltas represent small changes over the circle, and we know that motion is happening, we know that these must be small changes in time. So let's take this equation And let's divide both sides by a small increment of time, so that we get delta V over delta T V1 is equal to a delta S over delta T R. Now, this is quite powerful because we know that we can highlight. On the left, we have a delta V over delta T, and on the right, we have a delta S over delta T. And if we let T become very small, namely that we're looking at points on the circle where this becomes a very small movement, then all of our deltas basically become derivatives. And since we're talking about a delta T, these can become time derivatives. This is now quite powerful because now we have the liberty to say that dv dt times 1 over v1 is equal to ds over dt 1 over r. Now, we just have to apply a little bit more physics here, and we realize that from our previous lecture in Chapter 9, we said that s was a linear distance. And so we can just call that what we did previously, which was x. But not only that, if we take the fact that t is small, then there was no difference between, if t becomes really small, v1 and v2. Namely, we could just call that a general velocity v. And if we do that, we can make use of the fact that we already have names for dv dt, namely this is the linear acceleration, and dx dt is the linear velocity. So plugging these into the above, our equation now becomes acceleration over velocity is equal to velocity divided by the radius. And now all I want to do is some simple algebra and solve this for the acceleration. And we get acceleration is v squared over r. This is a type of acceleration that we discovered from moving in circular motion. So we're going to call this a sub c, and then define a sub c as centripetal acceleration. And so we get something very powerful that was not necessarily obvious. By looking at the way circular motion goes, then we can conclude that we get a couple of different types of acceleration, namely 3 types of acceleration when talking about circular motion. A regular acceleration, which is a time derivative of velocity. That's the good old linear acceleration that we know and love. We get the linear acceleration is equal to alpha r, where alpha, we remind ourselves, was the rotational acceleration from the previous lecture, and now we get a new one, which we only could do by breaking these down into some simple triangles, which is v squared over r. Another way of relating centripetal acceleration to some of the other accelerations that are on here is we can do things like saying that we know that v is equal to omega r, and so writing this in terms of circular quantities, a sub c is the same as omega r squared divided by r, which is the same as omega squared r. So we now have multiple ways of looking at centripetal acceleration in terms of either the linear velocity v or the rotational velocity omega. Keeping with our nomenclature from this chapter, we're going to call this equation 26. Last but not least, we know at this point that the most important thing that we cover in this class is Newton's second law, F is equal to ma. So, since we now have a new type of acceleration, namely centripetal acceleration, which is v squared over r, which is due to rotation, then when we have an object undergoing circular motion, well, some force had to be the cause of that acceleration. And so we can then label F sub c would just be equal to m times a sub c, which upon plugging in a sub c, we see that F sub c would just be mv squared over r. And this is something that we have seen briefly in chapter 4, but now understand exactly where it comes from. Namely, this is our formula for centripetal acceleration. And this we will call equation 27. This concludes all the equations that we'll need to use for this entire chapter. So, using this, as well as the summary back up here from chapter 9, we now have everything that we could possibly want at our disposal if we were to just add these two equations into the mix. So for completion's sake, I will write them over here. We are now in a position to start solving a tremendous amount of problems with these. But again, the summary of the story is that rotational motion is nothing more than just linear motion in disguise of us moving around a circle at constant radius r. Using the link equations, it allows us to go back and forth from rotational quantities to linear quantities, and the only thing that was hidden in the mix that we needed to do a little bit more from high school geometry was the fact that something has had to have caused the rotational motion, and that we can attribute to some sort of centripetal force. Some of the sources of centripetal forces we will explore in the next chapter, the most popular of which is gravitation. Until then, ladies and gentlemen, I hope that you found that this useful. Please come to the next video lecture about solving problems with these equations, and until then, never stop thinking.